Good morning everybody. I am Dr. Uday Kumar Khan and welcome back to my class once again. Today I am going to discuss about the response curve of a series and parallel resonant LCR circuit, and I will be giving the demonstration on the experiment to find the resonance curve and to determine the resonant frequency, bandwidth, and finally to determine the quality factor of a circuit. Let me first give you the theoretical background behind the experiment to be performed. So I'll be giving you the slide presentation for my theoretical part and then I'll give you the demonstration. So the experiment has the heading Study of the response curve of a series and parallel resonant LCR circuit, and the idea or the aim of this experiment is to draw the response curve and to determine the resonant frequency of the LCR series circuit and the anti-resonant frequency for the LCR parallel resonant circuit, and to determine the bandwidth of the resonance curve, and finally to determine the Q factor or the quality factor of the series and parallel LCR circuit. And as usual, for this experiment the apparatus used are the following. We need an inductor. Here we have the inductor of the range 10 millihenry, 30 millihenry, etc. Then we need a capacitor. Here we have the capacitor of the range 0.1 microfarad, 0.22 microfarad and 0.47 microfarad. An audio oscillator with RMS amplitude in the range 0 to 5 volt, having a very good control knob with good amplitude stability, and the frequency range 0 to 10 kilohertz. And the speciality of our trainer board, it has a digital frequency counter, and the resistances available in the trainer board, actually discrete components are present here. So 50 ohm, 100 ohm and 200 ohms are available. And in the trainer board, an electronic AC voltmeter and electronic AC ammeter are attached. So entire experiment will be performed with the help of a trainer board having a digital frequency counter. Let me first explain you the functioning of a series LCR circuit, how the response curve of this series LCR circuit is generated. I'll be discussing that. So this is a series LCR circuit. I have inductor, capacitor, resistance and an AC source VI and an ammeter to get the value of the current in the circuit. So this is a series LCR circuit driven by an AC source of constant output with RMS voltage VR, and if the linear frequency of the source be small f and the angular frequency of the source be omega is equal to 2 pi into f, then the RMS value of the current will be obtained from this formula. IR is equal to VR upon root over RT square plus omega L minus 1 by omega C square, where this RT is the total resistance of the circuit, that includes the applied resistance plus R is the resistance of the inductor coil L. And if we plot the IR along y-axis and omega along x-axis, then the curve obtained is as follows. So it increases, then reaches a maximum value Im, and then it goes down again. This is a schematic diagram of the response curve, and this response curve is called the resonance curve. The current I attains a maximum value Im at a frequency omega 0 called the resonance frequency. If I go back to the slide once again, then this curve shows the maximum current is obtained when the frequency of the source becomes omega 0. This is called the resonance frequency. And the maximum current can also be obtained from the relation Im is equal to VR upon R, where this VR is the voltage across the resistance in the LCR circuit. And this omega 0, this resonance frequency, can be obtained from this relation omega 0 L is equal to 1 by omega 0 C, and this occurs at resonance. At resonance, what happens is the reactance of the inductor becomes equal to the reactance of the capacitor. Thus, omega 0 L is equal to 1 by omega 0 C, and finally the entire impedance of the circuit becomes resistive. Therefore, we get the resonance and the current becomes maximum at resonance. Therefore, this equation helps us to find out the value of the resonant frequency omega 0 is equal to 1 by root over LC. So far till now we have obtained the resonance curve and the resonant frequency. Now we will come to the quality factor or the Q factor of the circuit. We have seen the current response of a series LCR circuit falls from its maximum value on either side of omega 0. Therefore, the rate of fall of response with departure of omega from omega 0, that is, the sharpness of resonance, is usually expressed in terms of the quality factor or the Q factor, and it is defined as Q is equal to F0 by F2 minus F1 or is equal to omega 0 by omega 2 minus omega 1, where this F0 is the linear resonant frequency. As I discussed earlier, omega 0 is the angular resonant frequency, and F2 and F1 are the two half power frequencies. Half power frequencies means at these frequencies the current of the LCR circuit falls to Im by root 2, or the maximum value divided by root 2, or the power at this frequency becomes half of the maximum power. That's why these are called the half power frequencies. So if I go back to the earlier slide once again, then we'll find, so these are the half power points where the current becomes maximum upon root 2, and the corresponding angular frequency is omega 1 and omega 2 about the resonance frequency. So another way of finding out the Q factor is possible here that I want to discuss now. The Q factor or the quality factor can also be found by using the relations Q is equal to voltage across L or C at resonance frequency divided by applied input voltage. So that will be VC at resonance upon Vi or VL at resonance upon Vi. Therefore, Q is equal to omega 0 L by R or 1 by omega 0 CR. So this is another way of finding out the quality factor of the series LCR circuit. And another point is this resonance frequency we obtained, that can help us to find out L if it is unknown, because we have seen omega 0 is equal to 1 by root over L into C. If I know the value of the C and the frequency, then L can be obtained using this formula. L is equal to 1 by 4 pi square f0 square C, or 1 upon omega 0 square into C. Now I come to the next point, that is the bandwidth. So bandwidth is defined as the delta omega is equal to the difference of the half power frequencies, omega 2 minus omega 1, which is equal to omega 0 upon q. If we use the equation 5, this can be derived easily. Thus, the Q factor gives a measure of the sharpness of resonance. See, here I have plotted 3 resonance curves for different Q values. I have taken 1, 2, 3, curve 1, curve 2, curve 3, and the quality factors of curve 3 is highest, then the quality factor of the curve 3 is higher than the quality factor of curve 2, than the quality factor of curve 1. And what we find, the curve with quality factor Q3 is very sharp compared to the other curves, curve number 1 and curve number 2, because here the quality factor is highest. Thus, the Q factor gives a measure of the sharpness of resonance, and higher is the value of Q, smaller will be the value of bandwidth. So bandwidth is this, what is the width of this curve, that is the bandwidth. And hence, now if I look at the quality factor, this quality factor not only gives the sharpness of resonance curve, this also gives a kind of magnification. And what is that? That we'll see. So if the resistance R of the circuit is small compared to omega 0 L or 1 by omega 0 C, that means resistance R is small compared to the reactance of inductor or the reactance of capacitor, then Q may be large compared to unity. That I showed here in equation number 7. So if R is small, then Q is large. Thus, at resonance, the voltage across L or C may be many times larger than the input voltage. That is, in series circuit, there is a voltage magnification. That magnification will be across L or across C. So, if we measure the voltage across C at resonance and divide that with the RMS value of the input signal, then we will get the quality factor. Now here I want to show you, as the current increases or current gets magnified, then what happens to the impedance of the circuit with the frequency of the input source. So along this x-axis we have the frequency, and here we have the impedance. And what we find, impedance becomes least at the resonance frequency, and that least value is the resistance R applied to the circuit. So the impedance decreases, becomes least, and then again increases with the variation of the frequency of the input source. And one more thing is, the current in the series LCR circuit lags behind the impressed EMF by an angle phi, and that phi can be obtained from this relation. Tan of phi is equal to omega L minus 1 by omega C upon R is equal to finally Q times omega by omega naught minus omega naught by omega. Omega naught is the resonance frequency. And if we plot the variation of phase with frequency, then we get this kind of curve. This is for small q value. The solid curve is for small quality factor value, and this dotted curve is for large quality factor value. And one interesting thing is, for omega greater than omega 0, the circuit reactance is inductive in nature. And for omega less than omega 0, that means above resonance frequency and below resonance frequency. Above resonance frequency, the circuit reactance is inductive in nature, and below the resonance frequency, the nature circuit reactance is capacitive in nature. Next, these are the experimental data tables I am showing you because I will be using these tables for my experiment. So mainly for series LCR circuit, we have three tables. First table is to record the data for different voltages as a function of frequency. This voltage is across R, across resistance. Therefore, in the table I have to record the frequency in hertz of source, then I have to record the voltage, and finally we will get the RMS current of the circuit. And we can keep track of voltage across capacitor and inductor also, but this may not be needed, only VR will be sufficient. So we have to record VR, and finally we have to get the RMS current I is equal to VR by R. And the second table is from the response curve. So using table 1, we have to get the first response curve, that is y-axis I and x-axis omega. From that resonance response curve, we have to collect this data to find the quality factor. Resonance frequency you have to note down, and the maximum current you have to note down. The frequency in hertz at which, that means the lower half power frequency and upper half power frequency you have to find out. Then bandwidth will be f2 minus f1 and q will be f0 by f2 minus f1. Finally, alternate way of getting the q, quality factor, for the given circuit, that can be obtained by measuring the voltage across capacitor at resonance, and that recording should be done in the following way. So I have to find out first the resonance frequency, then RMS voltage applied to the circuit, then RMS voltage across the capacitor at resonance, that we have to record, and then Q will be Vc at resonance upon Vr. That we have to compare them. These two data we have to compare for our experiment, whether we are getting the right or not. So I have completed the series LCR circuit theoretical background. I will give you the demonstration, how to connect the circuit in the trainer board, how to get the data from the trainer board, how to plot the curve, and from that how to record the data in the table, and finally I have to compare the Q values, one from the resonance curve and other one from the calculation of voltage across capacitor at resonance. Okay, this is my resonance kit, trainer board. I have an oscillator of which amplitude can be adjusted with this pot, frequency can be adjusted with this pot, and frequency multiplier is here. It has 4 different steps. We can go up to 125 kilohertz roughly. And speciality of this board is I have a digital frequency counter. So this digital frequency counter gives the frequency reading. At present it is giving the frequency 4.34 kilohertz. So if I change the frequency, then this will display. So the variation can be seen here directly. Okay. And amplitude can be displayed if I connect this output with the voltmeter. That I'll show later. So apart from oscillator, I have a voltmeter, I have milliammeter, then I have resistance. 3 different resistances are there: 50 ohm, 100 ohm, 200 ohm. I have 3 capacitors: 0.1 microfarad, 0.22 microfarad, 0.47 microfarad. I have 2 inductors, 10 millihenry and 30 millihenry. And here I have a BNC connector. So if I want to take this signal out, and I will be able to display in the oscilloscope. So for that, whatever signal I want to get from this BNC, that has to be sent to this input part. So these input parts should be connected to the oscillator source, or to the resistance, or to the capacitor, or to the inductor, so as to get the BNC output. So BNC output has the input here. So if I apply the input, then only we can get the output. Then I have one breadboard here attached. If I want to connect loose components and build the circuit, I'll be able to do it. Then one more thing is, I want to check how the oscillator amplitude and frequency changes with the variation of the pot. So I have connected the oscillator to the voltmeter. So if I apply some frequency, okay, suppose I am putting something like 1 kilohertz roughly, and now the amplitude is 0. So if I increase the amplitude, it goes like this, and the frequency remains same. Okay, and what is the highest amplitude? This is the RMS value, basically RMS peak value of the oscillator AC signal, that is 4.45 volt. And second thing is, if I keep the voltage constant to a value something like 2 volt and change the frequency now, then what happens? So I am changing the frequency. It's starting something like okay, I am here and the multiplier is at 10, then I am at 5 hertz. Okay, now if I increase the frequency, okay, I have to once again set the amplitude. So if I set the amplitude to something like 2 volt, okay, and if I change the frequency, then now I have reached up to 120 hertz. Then if I change it to other level, something like, so here I am changing the frequency, increasing the frequency. It's now 1.41 kilohertz. This is remaining same. Then again I am changing to the next step. Then again I am increasing the frequency. Now it is 12.52 kilohertz. It's more or less same. If I set some amplitude and change the frequency, then the amplitude, RMS amplitude, remains almost same. So this is the primary thing should be maintained, because I have to scan the frequency of the source to something like few kilohertz. In that range, the amplitude of the oscillator should remain constant, so that I ensured. So if I change the frequency, then amplitude remains constant. Okay, next part is I have to complete the circuit for series LCR. So I am switching this off, and now I have to make the circuit. This is my circuit as I showed you in the slide. So I have the oscillator here, Then I have to go to the L. So from oscillator I am going to the L. I am taking 10 millihenry. Then from L I have to go to the C. So from the other end of L I am going to the C. I am taking 0.22 microfarad. Then from C I have to go to the R. So from the other end of C I am going to the R. I am taking 100 ohm. Then from R I have to go to the ammeter. Then from ammeter I have to come back to the source. Okay, so I have completed this circuit. Okay, I have already set the amplitude of the signal, RMS amplitude around 2.2 volt. Now I have to check what is happening with the variation of frequency. One thing is, with this particular combination of LCR, I have calculated series resonance frequency is something like around 3.2 kilohertz. That I have to check whether I am getting the resonance value, that means the current will be highest at this value. So for that I have to switch it on. So now I have to increase the frequency. So what I am finding here, so if I change the frequency multiplier, then what I find is my frequency is 56 Hertz and I am getting the current 0.18 or 2 less. Now if I increase the frequency, then it is increasing. Then it is increasing, increasing, but I have reached the end, 1.4 kilohertz, but I have to cross something like 3.1 kilohertz or so. So I have to now go back to the next scale. So I am going to the next scale and now I have to change this. It's increasing again. So I am increasing the frequency. Now I am increasing the frequency and it's increasing. Now I have to go slowly. I am almost near the resonance. So now what I find is, now it has started coming down. Okay. So what is the frequency now? I am somewhere like 6.51. As I told you, my resonance is occurring around 3.1. So I am just setting the frequency to that value and showing you that is the maximum current region. Okay. So I am getting the maximum here, 5.72, then 5.79, 82, 83. That 83 I get somewhere around 3.42 kilohertz. Okay. So if I increase the frequency, then this comes down and slowly goes to the zero value. So I am not changing anymore. So I have tuned it till the frequency 12.50 kilohertz. Okay, this is the first part, and second part is I will be able to show you this variation of current in the oscilloscope. So for that I have to take the voltage across resistance to this input part, and using a BNC I will be able to show you in the oscilloscope how the current reaches the maximum value and then goes down. So slowly it increases, reaches the maximum value at resonance and then comes down. That I will show you. And third part is to find the quality factor of this resonance circuit. So for that I have to take the voltage across L or C at resonance and I have to divide with the input value. that as I explained in the slide. So for that I have to connect, let's see, capacitor with the voltmeter. Okay, and I have to set the frequency to the resonance. So that was somewhere around 3.4. So how much is the voltage across capacitor? It is 1.28. So using this I'll be able to get the value of the quality factor. One more thing is, this resonance frequency can be accurately measured by plotting the response curve. So as I discussed in the slide, so recording the data from this trainer board, we have to plot the response curve, and then from that we have to calculate the resonance frequency from the curve, and then we have to set the resonance frequency here. We have to take the reading for the Vc at resonance. Then only the quality factor will come out accurate, and that will match with the experimental value. So this part is over. Okay, I am showing you the oscillator output in the oscilloscope. So if I stop it, so here I am having the oscillator output as a sinusoidal wave. I have given some amplitude to the oscillator, and now if I change the frequency, then what happens is amplitude remains same. So it is clear, if I change the frequency, so I have increased its maximum, so it has become like this. Okay. Now again I am reducing the frequency, and what I find is so when it is giving the output with the variation of the frequency, amplitude remains same. And second thing I will be showing you how the current becomes maximum during resonance. Okay, so I have given some amplitude. You have to look at how the amplitude is changing with the frequency variation. See, it's changing, it's becoming high. It is changing, becoming high. It's high. Now it is coming down. Now it is coming down. So it is again increasing. I am coming down the frequency. I am tuning it down. So it is increasing, 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 increasing. Now it is coming down. So it is increasing and then it is coming down. When the amplitude is maximum, then the resonance occurs, and looking at this oscilloscope signal, we can correctly find out where is the resonance frequency. So this series part is over. So I'll get back to the slide once again. So I have discussed the theoretical background behind the series LCR circuit and given you the demonstration for series LCR circuit. Now I'll be discussing about the parallel LCR circuit. So here is the schematic of a parallel resonance circuit. I have L and R in series in one of the branches, and then in another branch I have C. So this is a parallel combination of LCR, and then I have an AC source VI, and the current can be measured with the help of a ammeter. And here total current I is distributed among the two branches L and C. Therefore I is equal to IL plus IC. And If the Z be the impedance of the circuit, then the admittance of the circuit 1 upon Z is equal to 1 upon R plus j omega L plus j omega C, where j omega L is the inductive reactance and j omega C is equal to the capacitive reactance. The imaginary part of 1 by Z will vanish when omega C is equal to omega L upon R square plus omega square L square, or omega is equal to root over 1 by LC minus R square by L square is equal to omega 0 say. In this case, the source current and the voltages are in phase. Power factor is unity and the circuits is said to be in phase resonance, and omega 0 is called the resonant frequency, and omega 0 must be real. Therefore, R square by L square is less than 1 upon LC, or R less than root over LC. And the impedance at resonance is purely resistive and has a value R square plus omega 0 square L square upon R is equal to L upon CR is equal to RDC, where RD is called the dynamic resistance. And finally, at resonance, the peak current from the supply is called the makeup current and is given by I naught is equal to V naught by RD. And we note that when R tends to 0, then RD tends to infinity. In the previous slide, if R tends to 0, then RT tends to infinity, meaning that no current is drawn from the source at resonance. For this, the parallel resonant circuit is known as a rejected circuit. The minimum value of source current occurs at some intermediate frequency omega m nearly equal to omega naught. Then I come to the current magnification. The current flowing through the capacitive or inductive branches at resonance may be many times greater than the source current. Thus, in parallel resonance circuit, current magnification is possible. The RMS value of source current at resonance is IR is equal to VR upon RD, where VR is the RMS source voltage. The RMS value of capacitor branch current at resonance is given by ICR is equal to VR upon 1 by omega naught C. Therefore, ICR by R, that is the current in the capacitor branch upon or the source current at resonance, that is becoming equal to Q, that is the quality factor of the circuit. Usually Q is greater than unity, and therefore we have current through the capacitor branch Q times the current drawn from the source, that is we get a current magnification. And here I show you the variation of impedance with frequency, how the impedance varies with frequency. So it's opposite to the current variation, as current is minimum at omega 0 or intermediate frequency nearly equal to omega 0, then the impedance becomes maximum. That's why we get this kind of curve. This nature tells us that the phenomena of current being minimum at omega is equal to omega m. Therefore, this is not resonance, this is called anti-resonance. And this frequency is called the anti-resonance frequency. So here I showed you the current response curve where this current is minimum at omega m nearly equal to omega naught. So this is the anti-resonance frequency. And again I have the experimental data table for the parallel resonant circuit. Here I have two tables. One table is for to record the data for different voltages as a function of frequency. So in the table I have to record the frequency in hertz of the source and then RMS current flowing in the circuit. And from the response curve we have to calculate the Q factor. So for that we have to record the resonant frequency, maximum current, and the lower and upper half power frequencies, and then we have to find the bandwidth, and finally we have to get the quality factor. So I have completed the theoretical discussion Now I will be giving you the demonstration how the response curve data is taken, how it is recorded. So let's do the experiment. Now I'll demonstrate you how to build the parallel resonance circuit and how to get the results, how to record the data, etc. So this is my parallel resonance circuit as I showed you in the slide. So I have L and R in series first, then that series is in parallel with the C capacitor. So from this junction I have to connect the ammeter, then ammeter end will go to the oscillator, then oscillator other end will go to the this junction, C and R junction. And here I will be using the same values of L, R, C. So now first I have to make this L, R. So I have L, then I am taking the R, then R other end, okay, and it has to go to C, then I am taking the C, then from C it has to come to L, okay. So I have taken, once again I verify, L to R, then R to C, then C to L. So this part is over. Then I have two junctions. One is LC junction, that is this one, L and C junction, and RC junction. This is one. This is the RC junction. So I have to take any one of these two junctions. So I am taking the RC junction, and then I have to send it to the oscillator. So I am sending it to the oscillator. Then from the other junction, I have to send it to the ammeter. Then from ammeter, I have to send it to the oscillator. Okay, now we have to check the response of the circuit. So I have set the amplitude around RMS peak value is 2 volt, and I have taken L is equal to 10 millihenry, C is equal to 0.22 microfarad, and R is equal to 100 ohm. Now I have to check the variation of current in this milliammeter with the variation of the frequency. So I start with frequency 415 Hz, and now I am increasing the frequency. So my current initially is at 8.66, and as I increase the frequency it will come down, and then it will again go up above the anti-resonance. So I am increasing the frequency, and you can see it is going down. Now 1.27 kilohertz, I am at 7.87. Now 1.73, 7.17, 1.71, 2.18, 6.35. So it's going down, 2.72, 5.45, 2.78, 5.39, 2.87, 5.30, 2.91, 5.26, 3.06, 5.19, 3.24, 5.25. So it had started to increase. So I have crossed the anti-resonance. 3.34, 5.25, 3.53, 5.47, 3.6, 3.75, 5.80, 4.08, 6.59, 4.28, 6.99, 4.57, 7.65. So now as I increase the frequency, current value is increasing. So I have crossed the anti-resonance frequency, and the feature I showed you in my slide, now we are able to find it happening here. So if I plot the current with respect to omega along the x-axis, then we will be able to get the anti-resonance curve, and from the response curve we will be able to find out the quality factor as I discussed in the slide. So one thing only I want to mention here, that is, each time I change the frequency, amplitude should remain constant. We have to monitor it by some way. Get back to the slides once again. So I have explained series LCR circuit and parallel LCR circuit. I hope you all have enjoyed my class and you will be able to perform the experiment in the laboratory. If you have any doubts, please write to us through email. We will meet you again in the next video. Thank you. Thank you for watching this video. Have a nice day.